Good. So last week we discussed briefly about some introduction to the motor system. So here, the section 7, you can see about the basic classification of a number of electrical machines, which cover so many different kinds of the domain. So you can see in here, you have basic EV machine, mainly for electric vehicle application, but we can basically see that we have DC motor system. DC motor, actually, we got PM system and one system using the winding to do the loops. So they divided in the series connection and also the shunt connection. And then for the other side, we have some popular machine like the induction machine, which really popular, famous. And this one, we have the cage motor and one motor system. And another famous machine is called the reluctance motor, which we may spend some time with the reluctance motor, and which one of also really famous machine, highly safety. And we also PM machine called the brushless DC motor, which also one of the laboratory class we're going to examine what it is. So they are those important machines we go for. But you can see in this picture here, there's so many different type of machines. We have no chance, no time to learn all of them. We only see a few of them, which is important, famous machine we're going to spend more time. One thing we can see that will be about the air gap of an inductor. You see a motor or a transformer, they basically should have a magnetic core. But between the magnetic core, we have an air gap. The air gap is something we can able to control the magnetic flux transfer there. So it more look like resistance. You can see that between the rotor and the stator, they don't have any physical contact. They must be divided by some air gap. The air gap can be 1 mm, 1 millimeter, maybe 0.5, or this kind of scale. So even though for a transformer, some transformer without any air gap, they just all the magnetic core will be one piece. But sometimes we also see an air gap between them. So that's something we need to look into. So air gap will be inserted usually in a transformer, even the inductor, to control the magnetic flux inside. We can also use it to control the B field, so-called H field. That's some term we have been using. I think you all learned the BH hysteresis loop or BH curve for when you studied high school, maybe in the basic electromagnetics. So in here, we try to show you when we have an air gap, we are able to make it to avoid any magnetic saturation. Because when you see the BH curve, then the famous BH curve is this kind of famous curve loop, then there will be a chance that when you apply too high current to the coil, there will be a saturation. So air gap is something we can control that. And if without that kind of protection, when magnetic core go to saturation, we'll see that the permeability, that means the mu-R, that the term mu-R, will getting much lower because the metallization can be decreased its capability. We can also see that the inductance will get lower because the permeability will getting lower. So that's the thing we don't quite like to see that. So that's why we usually using air gap to eliminate that issue. Sometimes the inductor or transformer may have some DC go into the system. You see a transformer inductor really scared about the DC voltage. So the DC will have the accumulation of the magnetic flux inside to make the transformer saturate. So usually for AC transformer, we use every day for AC voltage conversion because the pure AC, the AC voltage should be symmetrical between plus and minus voltage. But however, if for some system, if they don't control properly or some waveform is generated by some power electronic, we may end up with some kind of DC offset. So in this case, we therefore have this kind of the issue of the DC offset end up with saturation. So we use air gap to eliminate that issue. If we don't do that, the unit may get very hot as well because of a kind of the magnetic flux. We get saturated, we get too high current to burn the winding. So that's what we're trying to do. So typically air gap look like a higher resistance to stop any saturation, to increase the resistance to the magnetic flux when you pass through the coil or pass through the magnetic core. For power application, as I mentioned before, usually really tiny, little bit 1 mm, or even though smaller than that. So in many motor, the air gap, we tend to make it as small as possible so that we can able to provide higher magnetic flux. You see a motor, when we have high magnetic flux, we are able to have higher torque or higher power. But because the stator and rotor are not touching each other, so we try to have a kind of protection, so-called air gap, in order to make sure that no physical touching. Because when a motor aging, then the bearing may not be too good. Somehow the air gap may not be continuously 1 mm, maybe sometimes higher or lower due to the fluctuation or aging. So that's why for protection point of view, we tend to put some air gap which will be safe and also able to prolong the nighttime. Make sure that you won't have any physical contact or the crash between them. So that's why air gap not only to protect the magnetic flux, but also for safety, but also to ensure that the rotor and stator don't any physical contact. So that means to design air gap was something quite important for motor design. But however, for transformer, which are kind of the motor but become a static motor, then we also need to think about that for the protection. So to look at the equation, then mainly we look into the reluctance equation. Reluctance, if you can see that transformer or inductor with magnetic core with an air gap there, it more look like a two component acting in series. Just like in this equation, the core and air gap will be putting together in series manner. So the equation of each one of them, we already showed to you mainly about the physical parameter in here, the length of the core and divided by the area and also the permeability. For air core, because the permeability for air core is equal to 1 unity, so that's why we don't have any mu-out parameter here. And the area for air gap, that will be something we need to look into. Usually the magnetic core, the air gap area, then is fixed because physical geometry for the core area. But for the air gap here, then why we use AC? Because usually the air gap area can be larger because fringe field. The field can go through different area of the gap. I can show you how this gap pen here. See if we're able to sketch anything. If we got not good, then the flux will actually go through here in perfect condition. But because of the air gap, the flux may also go through in this sideway. So in this case, the physical area of the cross-sectional area may be larger than you expected. But however, you can see that if the air gap is so small, probably then the fringe field here, this kind of fringe field may be getting less. And so that's why in many cases, you can assume this area, the core area, which is this area, and this area is air gap area, could be opposed to each other when the gap is really, really small. That's what we like to see there. So the inductance equation, we usually become the turns ratio square divided by the total reluctance. So you can see that in here, once we introduce the air gap here, you're able to control the inductance. We can actually make the inductance become smaller because we introduce more resistance in here. So that's how the equation should look like. All right, up to this point, any questions? So the purpose for the air gap, of course, you try to avoid any saturation and also DC bias. You can see that if we apply a pure sideway to a transformer, so there's a transformer to do that, then there won't be any DC offset. But you can see that in case any issue, if you have DC offset slightly, DC offset. So that will cause a kind of the accumulation effect in the transformer. So you see every time the sine wave will have a positive and negative, you're able to reset the magnetic flux, also become AC. But however, if you do a DC offset in here, what happens is the magnetic flux will try to the flux level here. You may like to go up, and then you may go back down to 0, and up and down to 0. But if a DC here, every time you may accumulate slightly of the DC component here. Eventually, the flux level will go up to quite a large level to saturate the transformer. That's the thing we don't like to see that. So that's why the purpose of the air gap is try to help us to eliminate any issue due to something uncertainty. For example, like your power source is not pure sine wave with this offset. Maybe your inverter to produce the waveform is not perfectly without any DC offset. So that's the thing we like to do. So that's how the other purpose of air gap, we try to eliminate the issue. To summarize what we have said here, then electrical machine actually consists of many domains, including the motor, generator, and even transformer part of the electrical machine. And these are important because it's the basic component for all the systems, including electric vehicle and robotic system. You see the electric vehicle, as I mentioned before, we have a few main motors, at least 2 main motors. And also there's more than, say, 50 motors for different parts of the actuation, like how to control the windscreen, how to control the pump system, maybe how to control the window. There's many actuation systems. A robot as well, there's many moving parts in a robot, like linear motor, rotational motor, and a lot of the control system. So that means if you want to study, understand more about EV and robot system, you must study electrical motor generator. Generator also important. For all the power distribution, you need to understand how to design the generator. Like all the wind power, you need to know how to design a generator. Efficiency for motor today is at least 95% to be sensible. If you design your motor only 90, 80% is not a good design. Most of commercial good motor should be at least 95%. And to design and control motor, we can understand how to control the moving part. For instance, need to control the torque and speed characteristic, how to control exactly how to monitor, measure the torque, and how to control the torque. You see, when we control a motor, we need to adjust the torque level so they're able to provide proper acceleration. Like the EV, we need to have a really good acceleration as well. I think that in the future, as I mentioned before, why we need to study motor? Because it's a key component how to convert electrical to mechanical. In the future, all the vehicles in the world will be 100% electrical transportation system. You see, today, all the vehicle, you can move on from 8% of the vehicle, go to 80% in the next 10 to 20 years. Robotic system will all driven by electrical machine and motor. All the power generation and the wind power will be also hydropower, also electrical generator. So you can see that the electrical machine is so important. Without that, probably we cannot survive. So we need to understand how to design them, how to control them, how to operate them. So that's why this lecture is coming here. So I think in the next 10 to 20 years, we need to go for more intelligent control, how to monitor and control all the electrical machine to fit the future. So I think robotic revolution is coming quite soon. In the next 5, 10, 20 years, everybody should have your own robot. We have an iPhone today, but I think next 5, 10 years, you should have each one has your own robot. So for the whole population here, we got about nearly 8 billion. So at least 8 billion of robots will appear in the next 20 years. So how many moving parts? A robot is not single motor. A robot at least about 10 motors within that. So we need to understand how to design a robot, how to control that. So that's so important. I think AI is so important. Even though with AI, you cannot design motor. You need to come to my class to know how to design the electrical machine. So that's why getting important. So other machine like here, or the flying vehicle here will be important. Not only that one, for marine application, electric boat, electric vessel is important. The EV is not only EV today. In the future, what do you think about the EV? Do you think that's four-wheel? No. In the future, the EV is not only the wheel. We're expecting the vehicle, the electric car will have limb like a spider vehicle. We can move. Not only a wheel, so simple. 100 years ago, when we first developed vehicle, we used wheel because simple. We've been using wheel for vehicle for last 5,000 years. But today, when we have a motor control, we can move the arm, we can move the limb, implement the spider concept in the vehicle. So the vehicle can therefore go up the hill much easier, maneuver much easier, to turn it, stop turning much easier. So that's why a real concept for vehicle is outdated. You just think about for the future vehicle that will be using other methods. So that also motion control. So that's why in the future, electrical machine is so important. We will change the whole concept of the mobility. So that's why we come to this lecture. How we're going to do that? How to promote the efficiency. If the moving part is high performance, high speed of how we do the job. So that means a motor need to at least 95% efficiency, maybe even higher. For this few years, we're expecting maybe go up to 99% efficiency. And the response time must be really, really fast. How to make the motor moving really quickly so that it's able to become a robotic part. So that's something we need to do. So that's a lot of work we need to do. So final remark will be, machine will be a core technology for the future moving part. How to interface between electrical and mechanical. Future must be electrical. It's the only technology today you can see how we control all the energy property with high efficiency. We do have sine energy, optical efficiency, but maybe magnetic, but the efficiency is really, really poor. Only a few percent, impossible. Mechanical system also really poor efficiency, but only electrical we're able to perform more than 95% efficiency. So that means the future must be electrical. The response time is really, really quick. So that's why future must be electrical machine system. So that's also foundation for all the innovation. Without this one, we only need will be using the motor, generator, and transformer to do all the jobs. So it's a going field. So if you come to my lecture, you learn the going technology, how we design a motor, generator, and transformer. That's all, right, for the first introduction for the course. Any questions? My class is not only teaching you the basic technology. All this basic technology, actually, you can go to website YouTube and easy to learn here. But my class here not only giving you a basic concept, I'll tell you which concept is most important and which concept can give you the concept leading to the future technology. That's what my lecture like. Okay. Good. So next thing to do will be go to next class. There's some kind of the references here. If you learn more and click the link, you can go to it. You can buy the book, but it's very expensive. You don't need to do that. Some material you can very easy to get it. A lot of references from the internet. So the next thing to do will be I also post a lab safety requirement to all of you. So I already post on my canvas. So you can have a quick look. Tomorrow we're going to a lab where you can go to SRD building 301. I already set up a shared file. You can fill in your name there. Have you seen that? Have you started to fill in your name? Let me see if that's still available. And let's see that. Go to the cameras in here. I separate my lecture into week 1, week 2, and so on. Every week we have some posting there. So lab group here, if you click this link, you say able to see this document. So we are attending. Maybe we got this number of the lab. So next tomorrow, start from tomorrow, we got transform 1 and 2 experiment. It's still setting up, right? And so we have group 1 to 4 and 5 to 8 here. Do fill the name here. Statistically, we have 3 persons in a group. So you fill your name here. So if you fill in the group 1 to 4, then you come in week 2, that means tomorrow. If you fill your name in 5 to 8, you come next week. So you come every 2 weeks. But in case you cannot finish it, you can still come again to see to continue. In the next week, I think we still have and some components you can try out. So basically how we do. So do fill in your name so that we can know who will be coming tomorrow. Yes.
The person view so you can edit the name.
You can.
Yeah, this view.
Okay, and
You can go into the link on the share on the.
I already shared that. I already now edit. Let me see why.
Go on to the share.
It's under your face. Yeah.
Where is it?
It's supposed to be top right.
Yeah.
That's behind the scene. Yeah, share.
Anyone with the link, right?
Yeah.
No sign in requirement. But you say anyone with the link and no sign in requirement?
Yeah, but
Click the share button. You should change it to a like edit.
if you click share.
Not the arrow. Like the main
Just the main button.
The world icon.
Yeah, the one next to it, to the left.
Which one? You come in to give me a hand.
This.
Oh, okay.
That should work.
Right. Okay, I missed that. Okay. So you try that and fill in your name, and then we can know who is doing what. Yeah. Wow, so quick. Okay.
Wait, are there 2 elements? What's his name?
You may also fill in your last name as well, in case you got 2 of your same name. Anyway.
Alright, we're gonna have to come.
So next topic we're going to discuss will be transformer.
Wait, Evan, are you in 2?
I'm in 4.
Or you're in group? Okay, group 1.
Okay, wait. No. But I'm also named Evan.
Oh,
You're also Evan. You're with 2 U's.
That's okay.
Wait, no, there's another one with 2 U's. There's two Evan losers. What do you mean there's 2? Wait, no, but I'm gonna go with 1 U. There's
You and you.
Yeah. We should have never happened to be.
I saw it.
Okay.
We're separate, different, guessing.
Yeah.
Yes, we're going.
That's not.
I just want to my last name. How do you say it?
I just know my last name. I'm gonna be confused. My name. Okay.
Piece of deal.
Yes. No, you're right. Nah, it'll be by that.
No, it's not.
Take this at you and it'll be good. Why do that? Actually, can I type this at you? Last year's 2 times. I know you're saying. I know you didn't think. It's okay. You guys can.
My computer is really slow, so
Oh, no, you guys did next.
I was stuck. Fucking cool. While everyone was doing that.
Anyway, it's like right for downward.
Yeah. My brother began same you started as well. They have
It actually hated me.
So this week 2 or this week 1?
Week 2, I think, yeah, week 2.
This is week 2?
Yeah, last week was week 1. Anyway, so we'll start to discuss about the transformer 1. So in this transformer, we're going to show you about some basic concept of transformer, and then we also some mathematical principle, some parameter, how we're going to measure it, and then we're also looking into the inductance. Then tomorrow he'll come to the lab, you're going to conduct some testing for the magnetic current. We also conduct some testing for the equivalence of how we do the measurements, the extending about the basic parameter for transformers. We also, in this chapter, we're also looking into some application, how to understand various part of the transformer. The key thing will be, I don't think I'm finished chapter for tonight, but however, you can go back to read the chapter, understand the basic parameter for the measurement. Because tomorrow we're going to do some measurement for the transformer. So that will be including some resistance and inductance for transformer. That's something useful.
Is there pre-labs and like procedures, things you need to do before we go to the lab?
Yes. And I think tonight I will upload the lecture for you to start to look through them. You can prepare it. I don't think you need to prepare for anything. And as usual, you just come to the lab tomorrow. The lab will be 2.5 hours, should be sufficient for you to do that. But tonight I will upload it, so you can have a quick look about what it is. So basically it will be, have you done any transformer testing in the past? So basically it will be trying to measure the conversion voltage and try to measure the parameter for the transformer. You got some machine, and then you can able to measure the resistance and inductance of transformer. I think you do learn something about inductance in the past, right? Yeah. So, and do you know how to use the oscilloscope? You know that?
Yes.
And the visuals observe the waveform. For example, like apply the sine waveform, and then measure the waveform. We also need to measure the phase angle, which is what picture and curve.
We did not at the very end.
So we're going to use the oscilloscope to conduct some voltage, apply some voltage to a transformer, and then we measure the current. We have current probe to measure the current, and then each of the voltage and current become a phase angle. Then you can use that to calculate about the construction and the resistance of the one. So you have more detail about tomorrow. You go through the lectures and then you can understand a little more about that. Usually the professor will come tomorrow, I will come tomorrow, make sure that you are good. And I found that in this university, all the professors doesn't go to that. I don't find them just after the lecture, you went for the other classes. But the professor goes to that. No, it's a TA. That's a TA, yeah. I don't think that's the right thing. I think I will go to that to see what we are doing for that.
Okay.
Yeah. So they can ask me a question, what's the so big behind it. So tomorrow you're going to measure the voltage and current to get the parameter for the resistance and also the inductance. And this side you can adjust the understanding of the transformer, also the internal parameter for the transformer look like. And then you can also measure the voltage conversion ratio. I think in this lecture, you also know that for transformer, the voltage and the current ratio has some relationship. So we're going to assess that. So you can do you also learn how to actually do your own winding for the transformer. You are not just buying the transformer, you have to put your hands to use couple wires to make up your transformer. So that's the thing you learn how to do. Actually, this is not an internal concept for a transformer. So after this class, after the lab, you should know how to make a transformer, build your transformer, then compare your transformer with your home transformer. And your house, I think there's so many transformers in your house. Now you select your charger, and now your power room, there will be one transformer. You compare it to see what they are. So anyway. Computer still too slow. My computer a bit slow. I need to quit the program to retry it. Anyway. I need to close some file. Let's see.
Just think about it. Just like dropping the industry. Before that, these console code to create a brand
I need to close more files so that I'm able to. I think too many files open in my computer, so it slowed down the whole. Yeah.
This is a standard to not play around. All the work which you have. They're just clear. Let's just. Well, go, I have function for one now. You see that? Don't need to figure out, we'll use some bits. You just use some battery in the deep end. It shows the best that. The higher dimensions, it's easier to just use the projection matrix. You make it using.
Anyway, so about that, yeah. So now then we need to examine again about a transformer. I think basically you know about a transformer. So in here we try to see what a basic major component for a transformer. Again, I think you all know there must be have winding, two winding, primary side, and also secondary side. We also have magnetic core, which conduct the magnetic flux between the two winding. And then one thing will be how we're going to measure the transformer parameter. Anybody can tell me what kind of parameter of transformer you're expecting? About you, what do you think? What kind of parameter for a transformer? Specification or transformer? Parameter? How many number of turns? Number of turns in the primary side, secondary side, that's important. And also the power, what is power level for a transformer? 1 kilowatt, 100 watt, 1 megawatt is power level, is basic. And frequency of operation, what kind of frequency? You see, we are now using 60 Hz in our PowerPoint. But so most of transformer, you see everything will be 60 Hz. But some transformer can apply for high frequency. As I mentioned last week, the robotic vehicle, maybe EV, we are not using 60 Hz. We are using much higher than that, maybe 600 Hz. The high frequency, the motor will become smaller. So that's one. We also need to understand about the frequency operation for transformer and motor. So that parameter we like to see. And this parameter, when we convert to some resistance and inductance as well. So that's an internal parameter we like to see either. So, and of course, voltage conversion ratio would be the same as the turns ratio. That's a really basic concept. We all know that. But we're going to examine how it look like between this correlation. And also, if a transformer is loaded, that means connect with some output, like output resistance, output power, then we can see the voltage conversion ratio. Would that be the same? Would that be vary with the load resistance? So that's the thing we like to see there. But anyway, again, to tell you, a transformer just like a static machine without any moving part. When it with the moving part, then become a motor. So that's how we differentiate between a motor and also a transformer. So why we need to study the transformer? Of course, we need to understand all the power grid, power distribution are basically based on the transformer. And all the machine concept are started from transformer. When we learn transformer, you can gradually understand more about a motor. So that's why they're all important. And there's a many special applications. You can see that like the welding system, some audio equipment, we actually use a lot of transformer, like your speaker. Somehow we also use transformer to match the impedance. So impedance matching, voltage conversion, current conversion are important component. So, and the content will start with some history, and then we look at, again, the gap the inductor have more equation, and understand about inductance. We also understand if we do have sinusoidal excitation, what will happen. Sinusoidal excitation is a basic thing we connect to a transformer, because today we're all using sine wave. But actually, we can use other waveform. So in tomorrow's lab, if you can try and use sine wave, if you do have time to finish that, you can try different waveforms, and then you can observe what happened to the transformer. What do you think? If you apply sine wave to the transformer, in the secondary side will be also sine wave, for sure. How about if you apply a square wave? Do you think you get square wave in the other side of transformer? What do you think? This is an answer, right? What do you think? Square wave input, do we get sine wave output or square wave or ununiform? Square wave. Where is 0 and 1? So that the transformer is amplifying the voltage, so I'm not very sure. You can be tomorrow. That's quite interesting, because we all thinking a transformer must be a sine wave input, because we've been doing it last many years. But if we change them into square wave, maybe triangular waveform, maybe some special waveform pattern, what will happen? You help me. So, of course, for the basic learning teaching here, I just show the basic sinusoidal excitation first. Basic thing we learn. And then we look into ideal transformer. You see, for undergraduate, we all just stick to ideal transformer, maybe with some parameter first. Gradually, when you go for higher advanced level, maybe postgraduate, will show you more complicated concept for transformer. But we start with ideal transformer first, and then you look into some typical or more common transformer you can see, and then we're going to make a final remark for the course. So here will be some history. I mean, quite interesting for the history. We did talk about history for different kind of inductor or electricity, and you can see that in 1831, Faraday's actually famous guy, he developed a principle for electromagnetic. So from him, we start to understand actually the correlation between electricity and magnetism. That's a quite important development. So that also gives us the basic concept to correlate all the transformer, generator, and motor together. So that's a very important development. And then after a few years, I mean, in 1881 to 84, and then Gola and Gibbs start to design the transformer. During that time, the transformer really not really effective. And also is open core design. Open core design, that means the core is open, not closed. At the moment, all our transformer core are either ring shape or square shape, then the flux can circulate inside. The open loop can be another solenoid. They're open. The flux need to go through our atmosphere, the air. And then that's a really not effective transformer, but after that, a few years, and then William Stanley developed this kind of another closed circuit transformer using the closed circuit magnetic flux to do that. They are more look like a reasonable transformer. And then for 85, then another guy also developed another effective transformer that has been commercialized in Europe. So this picture is still in one of the museum, the first prototype that Stanley developed this kind of the transformer. You can see that, look, magnetic core here, you can see that there's some winding here and not all the winding here. And then he clamped the transformer core using a screw here. So you can see how the picture of basic more than 150 years ago transformer. And then since then, we started to understand more about transformer. We try to set the standard, how to make sure the standard of transformer, how it look like, and also started to develop the three-phase transformer. So what we learn here basically are single phase, but actually most of the transformer out there in the market, in your house, in the power distribution line, they all three phase. You can see in the power distribution, you can see 3 wire there because they're three phase. Because we use three phase to distribute high power. So of course the transformer there being used must be three-phase transformer. You can see a little box next to the distribution line there, they are all three-phase transformer. But here we first learned the single phase. So that's how in 1889. So that you can see that's a development for all the transformer system. So now then you can see that transformer, we basically learn maybe from physics or from other junior course, we are using 60 Hertz or 50 Hertz. 60 Hertz are usually for low voltage, 120 volt. Like in United States, Canada, or Japan, we are using 60 Hertz. But some other countries, like in Europe, United Kingdom, or maybe in China, they are using 50 Hertz. The voltage more than 200 volt. So you can see that 50 and 60 are common frequency being used for power distribution. Then for the magnetic core, that's the most important element, which we use ferrite, one of the important core. Ferrite is one of the breakthrough for a transformer. You first need to be able to apply the transformer for really high frequencies, like megahertz, kilohertz, hundreds of kilohertz. Why we need to do that? Because we need to use high frequency to reduce the size of the transformer. I think I also showed you the important equation, right? I think that's the equation I always show to you. Energy equal to of inductor half Li square. I showed you last week. And the power equal to energy times frequency, right? That's a basic equation for all the energy storage. Then inductor is transformer inductor coil. So if we use really high frequency, that means the frequency increase, the inductor will drop. in the same manner. That's to say that today we are using 60 Hz for a transformer. We increase to 600 Hz. The transformer size can be reduced by 10 times. That's quite important. But we are not happy about only 10 times. We are using megahertz here. Megahertz, you see, a few 100,000 million times higher. So the transformer size can reduce in similar manner. So that's why today you can see your adapter, your transformer, is all the chargers, they're so small size. But when you check many years ago, 10, 20, 30 years ago, transformer really big for each of your computers. So make all the things. So that's why we go for megahertz transformer. You can see that today the transformer, we learn about 50, 60 Hz, but we also start already use high frequency transformer in megahertz region as well. Why we can able to do that? Because we are now able to control the AC source in much higher AC source, high frequency of AC source. Our 50 Hz AC source, 60 Hz come from normal generator, maybe coal-fired, hydropower that usually rotate at around 3,000 RPM or 3,600 RPM. That would be equivalent to 60 Hz. But when we like to go for higher frequencies, we can use power electronic to generate power source at much higher frequency, megahertz power source, hundreds of kilohertz power source. So that's the case. We can use the high frequency method to couple to the transformer. So we can therefore use this kind of MOSFET to create high frequency power source. So that's what we are now, the technology we are now using for power conversion. So high frequency AC with something quite interesting. So that's another new research topic for high frequency AC distribution. Today we are using low frequency 60 Hz power distribution. This is a lot of research. We tend to use high frequency AC distribution, like 60 kilohertz. That's typical things. So many of the new electric vehicle or maybe new aircraft system, we're using high frequency AC. And DC as well, we are also using DC power distribution as well. So that's why we all need to use the high frequency transformer technology to do the work. So the key advantage why we use high frequency, because smaller size, high power density, we can reduce all the physical size for transformer in a way inversely proportional to the frequencies. And because of this one, we can also eliminate a lot of the copper, reduce the copper. Before, our transformer can be 500 turns, but nowadays for high frequency transformer can be a few turns. I can see many transformers only one turn. So you can see that we can reduce the material, reduce the copper probably we can reduce the power losses. So that's something quite interesting. We can also looking into the application for transformer, including power supply, like I mentioned about the charger, the phone charger are using transformer, high frequency transformer. We are also all the coupling high frequency radio wave. We are also using high frequency transformer, renewable energy like the solar power, wind turbine. We are also using a lot of the transformer. Electric vehicle like the onboard charger, we also need transformer. Why is that? Say our charging system for our wall plug here 120 volts. Some of them may be 200, but the EV battery, I think you all know that the battery today, the latest battery voltage for electric vehicle is. Anybody can tell me what's the voltage for the electric vehicle? I think I told you some time ago, right? For the battery for inside the electric vehicle for the latest model, 95, 96. It's like 48 or 96. 800 volt. 800 or 800. So 800 volt. Even Tesla, the old technology still using 450 volt. The latest models will first use 800 volt. Why is that? Because we need high power. Oh, when we want to promote high power, only thing we can do is the voltage. Because the current is quite critical, high current need, break the cable. That makes sense. So the only thing to do is to increase the voltage. But you can see that our wall plug here only 120. over 800 and go up to 800. So we can use transformer to increase the voltage that becomes for the charging. So that comes to our vehicle from board charger and also off-board charger to this transformer to increase voltage for the charging. So that's also requirement for transformer too.
It's taking that much power, right? Would the battery be able to handle it though?
Today, the electric vehicle, you see the power level, the energy storage power level, something like the common low-cost vehicle, 50 kilowatt hour. For more expensive one, will be 100 kilowatt hour. For buses, 200, maybe 300. So you can see that even though our charger using 10 kilowatt, by simple calculation, we need quite a few hours for the charging. So nowadays we do supercharger, that would be so-called supercharger, at least 50 kilowatt. If you go outside to the supercharger, the test number will be some of them 100 kilowatt, 200 kilowatt. So that's why they can charge the vehicle within 30. But in the future, if you want to get much higher power, then you need the battery to be even higher, like buses, Norway. The battery needs must be at least 100 kilowatt hour. Then we need to charge up with much higher power charger. Then the thing is the current used by cable. You can calculate 200 kilowatt. The power for 200 kilowatt basically, the power equal to V times I, right? Maybe you can put the root 3 for 3 phase. Then that means if you say 200 kilowatt, right, equal to root 3 times the voltage. For instance, we use 200 volt times I. What is the current? If you have calculator, you help me to current. I don't have calculator. I guess the current. Talking about hundreds of things. You see this kind of the cable here. Of course, it is HDMI, but normal power cable at our house usually about 15 amp for this kind of size. But if you increase this current to about 200 amp, that means this cable, this will increase the 5 by 20 times, 50 times. The cable will that thick. You don't think it's feasible you can use that thick cable to charge your vehicle? Too heavy, too inconvenient. So we need to use other new technology. We need to increase the voltage, much higher voltage, and lower the current. So that gradually we need to increase the voltage. So before the charger, we first need use transformers to increase the voltage to much higher voltage to reduce the current. So today we are using this technology, but tomorrow we may demand for high power for the vehicle, high power for the robot. In this case, we need to increase the voltage further for the battery inside. So that's the technology. How to do that? We use power transformer to increase the frequency, increase the voltage. We use a high frequency transformer, high frequency magnetic transformer to do the job. That's what we do for the experience. So that's basic concept about transformer. But firstly, we look into the gated inductor to understand more about the equation for the gated inductor. We learned briefly about last week or just now. So here we try to learn a bit more about that. So our magnetic core are basically with this kind of winding in here, magnetic core in here. Sometimes we have air gap and zero touch each other, sometimes with air gap. So you do an air gap, you look like if you change them into the equivalent symmetry, the winding here we call this driving force, driving energy, driving force. The terminology here we call it MMF, metromotive force. I think I mentioned this time to you. So the equation is N number 1 times I. So you can see that I, although look like a current, but N times I is called MMF in the teacher for mathematics. That's a common name we all use. You look like we're driving the current, driving the magnetic flux inside the transformer. We call the driving force also MMF. And this kind of driving force won't look like a supply to energy on two resistance here. One resistance we call the field magnetic core. One resistance is the air gap, but we don't call it resistance. into it, and then they call it the reluctance. That's the term. So that means these two are correlated in series. So that's why I'm putting them in series. The floating energy here is the magnetic flux. They have called them the general magnetic flux. The flux will pass through the magnetic core plus the air gap. So the floating quantity, we call them the flux. The symbol we usually using 5 to represent that. So you want to look like Ohm's circuitry, I think you learn Ohm's law, right? The driving force here, look like voltage driving through resistance, you're going to current the current now, the pointing magnetic force. The driving force, low voltage, we call it N and N. The equation of N and I. So we can see the correlation between the voltage and current anyway. So if you go for any website, any textbook, you can see a comparison between electrical circuitry and magnetic circuitry, which we also mentioned sometimes. Right? But anyway, so the equation for the reluctance will be given by this kind of the physical parameter for the geometry of the shape, like the length of the unit, and also the area, and also the permeability. So with this magnetic core, the mu will be related to the permeability of the material. If for iron use a few thousand, for air will be 1. So that's how we do that. And the equation that's really much look like also voltage source or power input divided by the resistance or reactance here. And then the density, B represents the magnetic flux density. In density in the unit area. It's straightforward, very simple. You can actually correlate all these equations to what we learned in the past. Like simple density or like the electrical circuitry, they're all similar, but we use other term, other new terminology. So resistance become reluctance, current become flux, voltage become N. That's all. And in here, you can see that I use the AC area of the core for area of the air gap. As I mentioned before, I just assume the fringe field to be really small, so these two areas are similar. If you don't do that, because they are very difficult to estimate exact area, how the magnetic flux will go to the air. So we usually say, if a good machine, if the field don't go outside too far away, then I assume these two areas the same. So I'll show this kind of thing, then you can see the D field will be look like similar. These two flux, the flux here pass through here and pass through air is the same kind of the flow, same kind of curve, same kind of flow. So that's why these two equal, right? The same kind of the curve, same kind of the flux go through. So that's why they can be the same. So that's how we understand a gapped inductor. Any comment, any question here? Yes?
What's the space time on the question?
Say again? A area. Area, sorry, I forgot about that. Area is the cross-sectional area for the core. A is the area, cross-sectional area for magnetic core or the area. So let's see a quick example. If you go magnetic circuitry, it mainly use it as a relay. Relay then energize them, we just couple them together, they have some moving parts. And then number of turns is finally used for winding, and the magnetic core length. So this length will be 360 mm. The air gap is 1.5 here, they get 1.5. But actually then they will close the circuit. So given the magnetic flux density, we just say the density H field. So magnetic field, we got B and H. So we all seen the H field in the past. The H field magnetic field intensity is 910 N per meter. And then calculate about the current in the coil, compute the permeability and relative permeability of the core, and also with the radius close, what kind of current should needed to produce the flux, say 0.8 Tesla. To do that. So that is a very simple example how we make use of the simple matrix equation I showed you just now. So the answer here will be, so if the B field requirement in the core is 0.8 Tesla, then H field requirement is all given, is 510. Then the MMF, the driving force, we have an equation in H field, the H parameter, multiplied by the length of the core. So that will be 510 multiplied by the length of 0.36 meters. We are going to 6 meters. So that gives us a MMF equal to 154 MPa. You see, the people sometimes they say T the same number of terms. But actually, number of terms have no unit. So some of you just do say 184.8. Some people put a T there because T doesn't mean anything. So the are optional. Bigger number of terms, as I mentioned, is no unit. And then the air gap MMF will be using the H parameter, H intensity, multiplied by length of air gap. That means inside the air gap, we also have its own MMF. We have two air gap here, which one here, one here. So we can multiply by 2 here. And then that gives us the air gap MMF is 1910. So total MMF, you see MMF more look like the driving force. So two driving force connect together in series, then we can see the total driving force, the total MMF equal to this one plus this one equal to 2094. So now then we got this driving force requirement from the source, from the coil. So that means this coil is 2000 something, and we divide by number of turns will be equal to the current requirement. I think you remember Ni is the driving force. Our equation here, yeah. Ni is the driving force here. So if we know about the number of terms, then we don't calculate current, we need to calculate the total MMF first. So now then in this equation, we already calculate the MMF, and then that's why we can obtain the requirement of the current. That is the electrical current we need to apply for the coil to produce that kind of driving force. We call it MMF. That's the driving force. So that's how we get that. And you can compare that. You can see that when we apply to the coil for that kind of MMF, we produce 2 MMF, once in the magnetic core, one will be in the air gap. So you can see that the air gap has a much larger distribution of the MMF than the core. So there's some phenomenon we can see. Whenever we have air gap, along the driving force, you go to the air gap. This concept look like when you have two resistors connected in series, the higher resistance you receive more voltage. I think you got the concept. Same like in here, air gap more resistant, but of course we call it reluctance. Can receive more voltage. Then need more MMF here. So anything we learn here, in think about what we learned in the electrical circuitry, it's the same concept. Very simple, but very easy for you to formulate. Get that? Maybe in this lecture, you're a bit new to you, then you can go for example, a few examples here, then you understand much better. But this topic is really straightforward, very simple. It's a medium of the literature in the internet website. We're able to get more material. So B will be the permeability for the mu. So B divided by H is the permeability of the unit basic equation. So two main from the equations. Although in some I don't require you to remember anything, but some unit basic equation like this also magnetic also right, and also B and H coherent you need to remember. And then we have the B field difference from A, and the core we have 510, then we can expect the permeability to this one. You see mu C is the permeability, but the actual equation is equal to mu naught is the free space permeability, 4 pi 10 to minus 7, and then remember this term, yeah, and about then we therefore obtain the relative permeability of material. So mu R is more commonly known. For example, each material will calculate about this parameter. Now, if we say our air here is 1, some kind of the iron a few hundred, maybe a few thousand. For ferrite will be 3,000. So now then you can see this core material will be 1.50. So the part 3 will be, say, if the relay is closed, that means here is closed, the air gap becomes 0. Then what is the current to produce the same kind of the flux? So now then, if the air gap becomes 0, of course, this term, the air gap MMF disappear. You're not present there anymore. Then we only have the core contribution for the MMF. So that is this term, 500. So this term times the length of core equal to this area is the same as before anyway. So the amount of the energy to drive the relay is the same. So we have less air gap. We don't need additional MMF to dissipate in the air gap resistance. So all of them will be coming from the magnetic core. So we only need the same kind of 184 as before the N-channel coil. So now that only have this one, the current will be much smaller and reduce the current to 0.36. And before we create high current, and now we with the air gap, you need this current because this current is to produce the air gap force. But now without air gap, the current becomes small. So that's why you can see the difference between how we actually relay with and without air gap. Okay, any question? You see this question is very straightforward. We only have a few equations here. For example, like pH equation, right? Where is phase equation? These are very basic parameter for permeability, and then you see the MMF H times length is also the MMF, and I also the MMF. So we got a few basic equations here, which we think will be know how to operate and manipulate with them. So inductance. Before we have magnetic circuitry, but now then we like to talk about the inductance. When you have a winding coil, you have machine plug in there to measure inductance. Inductance, the unit is called Henry or H. Yeah. I also mentioned H is really large quantity. We use it using mH to measure it. So unit is called H, but it's too large. We use milli Henry to usually to parameterize our inductance. So we got a term called the flux linkage. That means all the flux pass through them, but one term will linking one term of flux. But when they're putting more and winding, more term will link by this particular flux. So N5 will be so-called the flux linkage. So that means to say, you can see that just now because Ni is the MMF, more number of turns, you can have more force, driving force. So that's why number of turns actually controlling the input voltage. So that's why we can understand more the flux linkage, how we link the flux properly using number of turns. So that's why comes the terminology called the flux linkage. If you like to learn any magnetic, then flux linkage also important. Although I don't try to spend too much time on electromagnetic, I think next semester will be the similar after you've got the electromagnetic podcast. If you like, then that's also quite important. But electromagnetic is not taught by me, by other professors. Anyway, so here with some new terminology. So the flux linkage, you need to memorize it. For basic definition for inductance, we therefore flux linkage per unit of the current. So that means from equation point of view, you see flux linkage divided by current will become the inductance. So the B field equation, the flux divided by area is the magnetic flux density. And then that's why it can be, we also, the basic equation between B and H are correlated by the permeability. So if you put all these things together into this equation, then you end up will be the first linkage, the mu. We have n and phi here. Phi will replace by this equation, become this one. H we can also replace by b and mu. So then we can end up with this important equation. N is proportional to n squared. So you can see that many of inductance, most 90% of inductance are proportional to the number of turns squared, like in this equation. So you can check this equation, you can see that it's n squared divided by the reluctance of the core. So that is a really famous equation for inductor. If you do any inductor construction, then you should base on that is to say you can make number of turns there, and then you can see what's the cross-section area for the inductor, and try to get from the literature what is the permeability, and divide by the core length, then that will be the inductor. So you can also try tomorrow if you have inductor, then you can using this method to calculate the inductor. So of course you can compare with your measure. So this is very famous equation as well for inductor. So let's see a quick example. Yeah. So our magnetic circuitry as shown in here. Then we have a core length. This length will be 50 centimeter. We do have a little gap of air gap will be 1 mm somewhere here. And the cross-sectional area, this area, cross-sectional area, 15 cm squared. If we assume the air gap area same as the core area, make the circuit simple. And then if the permeability of the magnetic core will be 3000, driving 1 m. So let's calculate about the flux and flux density of the air gap and the inductance of the coil. Then that's the thing. The definition for reluctance are based on physical parameter like the length of the core and divided by area and the mu parameter. So just now we have the core length 50 in here. The mu r is 3000. Mu naught will be 4 pi times 10 to the 7, and area AC, which we also have AC 15. We just directly plug in here, we'll just directly can get the reluctance. For air gap as well, air gap length will be 1 mm. So we can put in here, we get this also the reluctance. And then the flux, the flow parameter is the driving force, like the voltage divided by the resistance, the reluctance here. So we got 400 amp number of turn here. Do we have number of turn here? And current 1 amp, then we can 1 amp here. Then we assume we got the 400 number of turn, then we can get the driving magnetic flux in here. The flux unit are using Weber here, WB Weber. And then the density will be the flux divided by the area, which is 0.43 Tesla. So that will give you the magnetic flux here. I feel probably I missed out the number of turn parameter here. So the number of turn in here will be 400. I think I missed something here. I will update it after the lecture. So that's how we calculate the B field inside the core. But for the inductance, as I mentioned, because n squared divided by the reluctance. So we have two reluctance here, number of turn in here. So that's why I quickly can calculate the inductance. Inductance have many formulas to calculate. The other formula will be the flux linkage divided by current. We can do the same method to calculate them. So that's not quite a few equations, but the answer will be the same. So that gives you an understanding about how we calculate inductance, reluctance, and also based on something related to Ohm's law to calculate all this magnetic structure. Any questions? Good. So we'll continue in every time. So tomorrow, then we'll come to the class and understand more about it. Okay. So see you tomorrow. Half of you go to class tomorrow, right? See you then. So tonight I try to upload the lecture. We still try to do the final touch up. And then that's all. Thank you. See you then. Okay.
What's Professor Chang?
Hi.
You were talking about you know,